Hello everyone and welcome to our module on blood flow mechanics. There are lots of mathematical equations that describe the flow of fluids through vessels like blood vessels in the body, but there are basically two that have importance when it comes to cardiovascular physiology. So the first important equation that has to do with blood flow through vessels is simply called the flow equation, and it derives from Ohm's law. So you probably learned Ohm's law as it relates to electricity in a physics class, but it also relates to fluid mechanics and blood flow. So Ohm's law says that the voltage in an electrical circuit is equal to the current I times the resistance R. This is just basically a simple expression of a fact that if you want to drive flow through a system, whether it's electricity or fluid flow, the amount of energy you need, that's the voltage, is equal to how fast you want to go, that's the current, times the resistance to flow, that's R. So we can modify Ohm's law and apply it to fluid flow like the flow of blood through a blood vessel. And if we apply it to fluid flow, the change in pressure in a system is equal to the flow rate Q times the resistance R. And this equation is often applied to the body as a whole because the entire cardiac output flows through the body as a whole, and therefore the resistance to flow is equal to the total resistance of blood vessels in the body. And we'll talk more about this later on in this video. So when we're talking about the body as a whole, the change in pressure as blood flows through the body is equal to the cardiac output times what's known as the TPR. TPR is total peripheral resistance. It's the sum of the resistances to flow of all the vessels in the body. So if we put this all together, we get the flow equation, which says delta P equals cardiac output times TPR. And we'll be coming back to this more and more throughout the course of this video. And just to make this more clear, let's imagine that we have a blood vessel, and let's imagine that we have a pressure of 10 as blood flows into the vessel, and let's imagine that when blood flows out of the vessel, we have a pressure of 5. This change in pressure of 5 is equal to the flow rate Q, the flow rate of fluid moving through that vessel, times the resistance R. That's the flow equation, and we're going to come back to this more and more as we go through this video today. The second equation that's important for physiologic flow of blood through the body is simply a geometry equation. So the velocity of blood moving through blood vessels times the area of the blood vessels is equal to the flow rate. So this is just a mathematical, geometrical sort of equation. The velocity in meters per second times the area in meters squared equals the flow rate in meters cubed per second. So just like the flow equation, we'll come back to this geometrical equation later on in this video. Now let's talk about two important concepts that relate to the flow of blood through vessels in the body, and those are the concepts of resistance and compliance of blood vessels. When blood flows into a blood vessel, some of those vessels are very, very stiff, sort of like a lead pipe. Other vessels are very distensible and stretchy, and they can stretch to absorb the fluid as it moves through the vessel. Vessels that are very stiff have a high resistance to flow, and they also have a low compliance. The term compliance means the distensibility of vessels, and resistance and compliance are related. So stiff vessels have a high resistance to flow and a low compliance. They are not very stretchy at all. Stretchy vessels have a low resistance to flow and a high compliance, and these are the two concepts of resistance and compliance that are important to blood flow mechanics. High resistance vessels tend to have a low compliance and vice versa. One of the classic applications of the concept of compliance to cardiovascular physiology is the pulse pressure. The pulse pressure is the systolic blood pressure minus the diastolic blood pressure, and in a normal patient with a blood pressure of 120/80, the pulse pressure would be equal to 40. It turns out as we age, older patients develop an increase in the pulse pressure. It also turns out that patients with hypertension develop an increase in the pulse pressure. And the reason for this is because older patients and hypertensive patients have a change in their vessel compliance. They have decreased compliance of their blood vessels, and this leads to a rise in the pulse pressure. To understand this better, you need to appreciate that the compliance of a blood vessel can actually be calculated as the change in volume divided by the change in pressure. So let's consider a stiff blood vessel, which, as we said before, has a very low compliance. These types of vessels have a high pulse pressure. So why is that the case? That's because a small change in volume is all you get for a given pressure applied to the walls. Let's look at this equation at the bottom of the screen here. So the compliance is equal to the change in volume in a blood vessel divided by the change in pressure. If we rearrange this for the delta P, we see that the delta P is equal to the change in volume divided by the compliance. Now, any blood vessel needs to get a constant change in volume through that vessel. Think about your body. You need to get your entire cardiac output through your body no matter what the compliance of the vessels is. So if you want to get that same change in volume through a set of blood vessels that has a very low compliance, the only way you are going to do this is by raising the change in pressure as blood moves through that vessel. So by this equation, you can see that when the compliance goes down, the delta P for a blood vessel must go up in order to move the same volume through that blood vessel, and that's why the pulse pressure increases when you have stiff vessels that have low compliance. The opposite is true for stretchy vessels. Stretchy vessels have a high compliance and they tend to have a low pulse pressure. That's because you get a large change in volume for any given pressure applied to the walls. And here's one more way you can think about this to keep it straight in your mind. The pulse pressure varies with vessel compliance, as we've been talking about, and stiff vessels have a low compliance. So let's imagine we've got a very distensible vessel, a stretchy vessel, and we shove a bunch of blood into that vessel. Well, because the vessel is stretchy, it can absorb the blood volume without increasing the pressure so much. So we get a normal blood pressure and a normal pulse pressure, like 120/80 with a pulse pressure of 40. Now let's imagine we've got a very stiff, rigid vessel. You tend to find vessels like this in older patients and patients with hypertension. Well, now when we shove this blood volume in, the vessel cannot stretch and distend. Therefore, the pressure inside the vessel goes up a lot. These molecules are being packed close together because the vessel cannot stretch. Therefore, we get a higher pulse pressure and we get a blood pressure like 170/100 with a pulse pressure of 70. This is what you see in older patients and patients with hypertension. It all ties back to the concept of compliance. Now let's go back to that flow equation I talked about at the beginning of this module and talk in more detail about the concept of total peripheral resistance. So like I told you at the beginning of this video, the flow equation states that delta P is equal to blood flow times resistance. And when we're talking about the entire body, the blood flow through the entire body is the cardiac output, and the resistance to flow, the resistance contributed by all the vessels and organs in the body, is called the total peripheral resistance. And anytime this total peripheral resistance goes up, it means the heart has to generate more pressure to maintain flow. In other words, if peripheral resistance goes up and we want to keep the cardiac output constant, then we have to raise the driving pressure. And when the heart needs to create more pressure, it means the heart has to do more work. So anytime the peripheral resistance goes up, anytime the total peripheral resistance of the body increases, the heart has to do more work to drive the normal cardiac output through the body. So just to emphasize this point, when it's easy to push blood out of the heart, less oxygen is required by the myocardium. When there's an increase in the resistance to blood flow through the body, in other words, when the total peripheral resistance goes up, then the heart has to do more work and the heart needs more oxygen. So what are the things in the body that affect the total peripheral resistance? In other words, what makes it harder for blood to flow out of the heart and through the body? Well, the first thing is the types of vessels, the pipes and tubes. The second thing is the thickness of blood, and this is called the blood viscosity. So there are many different types of vessels in the human body. Some of them have a very high resistance to blood flow and others have a very low resistance to blood flow. And the way you can best appreciate this is by looking at the pressure change as blood flows through vessels in the body. So as blood leaves the heart and flows through the aorta, the blood pressure falls to about 100 millimeters of mercury systolic. As that blood moves into the large arteries, there's only a tiny change in pressure, just a few millimeters of mercury. And this is because the large arteries provide very little resistance to flow. Remember what I said before, when there's high resistance to flow, you're going to have a high delta P, or a big pressure change. If you've got a very low resistance to flow, there'll be a very small pressure change, and that's the case in the large arteries. As that entire cardiac output moves from the large arteries to the small arteries, there's a pressure change of about 10 to 20 millimeters of mercury. But the biggest pressure change occurs when blood passes through the arterioles. The pressure change across the arterioles is about 35 millimeters of mercury. And I've highlighted this in red because you should remember that the arterioles are the set of vessels in the body that provide the greatest resistance to flow. They are said to be resistance blood vessels, and the pressure change will always be highest across the arterioles compared to other types of blood vessels that also see the entire cardiac output move through them. So I've summarized these points on this slide. The arterioles are said to be the resistance vessels. They are the major determinant of the total peripheral resistance. There's a large pressure drop or large pressure change as blood flows across these vessels. And as you may know, the autonomic nervous system can modify the arterioles and shrink them, that's called vasoconstriction, or enlarge them, that's called vasodilation. And when these vessels shrink, the resistance goes up even more, and when these vessels dilate, the total peripheral resistance falls. Viscosity is the thickness of blood. Think about the difference between water and maple syrup. Water has relatively low viscosity and therefore it flows easily through a vessel with low resistance to flow. Maple syrup, on the other hand, is thick and sticky and therefore it has more viscosity and greater difficulty flowing through a blood vessel. There will be more resistance to flow when pushing something like maple syrup through a blood vessel. Most of the blood in our body is made up of water and the viscosity is relatively low, but there are a couple of pathologic conditions where the viscosity may be higher or lower, and this can affect the resistance to flow. So first of all, patients who are anemic have relatively fewer red cells in their blood, and this can lower the viscosity and therefore lower the resistance to blood flow. A number of pathologic conditions create a high viscosity situation. First of all, polycythemia. Patients with polycythemia have excess red cells and sometimes also white blood cells and platelets, and this can raise the viscosity of blood and increase the resistance to flow. The same is true in multiple myeloma. Patients with this condition have lots of extra proteins in their blood, and therefore the viscosity of blood can go up. And then finally, spherocytosis is sort of famous for being a high viscosity situation in terms of blood flow mechanics. Patients with spherocytosis have red blood cells that form spheres instead of the normal biconcave disc. These cells are more rigid and they don't deform normally as they move through capillaries. That makes it harder for blood to move through the vasculature, and that raises the viscosity of blood and the resistance to blood flow. Poiseuille was a French mathematician, and he created Poiseuille's law, which describes how the resistance to flow varies with certain elements of a system, and this law applies to blood flow through the human body. So remember that the flow equation says the change in pressure is equal to the flow rate times resistance. We can rearrange this equation and solve for resistance to flow and state that it's equal to the pressure change divided by the flow rate. Well, Poiseuille's law further relates that resistance to various elements of a system. So Poiseuille's law says that resistance is equal to 8 times the viscosity times the length of the tubes that blood is flowing through, divided by pi times the radius of the blood vessels to the 4th power. So we've already talked about how when viscosity goes up, resistance to flow goes up, and that fits with Poiseuille's law. The other important element of Poiseuille's law is the radius here. Remember, radius is in the denominator and it's raised to the 4th power. So changes in radius have a very powerful effect on resistance. When the radius of a blood vessel falls, the resistance to flow is going to go up a lot because radius is to the 4th power. When the radius to flow increases, then the resistance to flow is going to fall significantly, once again because radius is raised to the 4th power. Now let's talk about series and parallel circuits. So the organs in the human body are arranged in parallel, and this is a very good thing because by arranging organs in parallel, you greatly reduce the resistance to flow, and this makes the heart more efficient because it doesn't have to generate so much blood pressure. So when blood leaves your heart, if our organs were arranged in series, the blood would then go to the kidneys, for example, and then to the gut, and then to the liver, and then it would all come back to the heart. This would be bad because the resistance to flow in this system would be very, very high. Instead, what happens is that blood leaves the heart and then it branches and flows through organs in parallel. So some goes up here, for example, through the kidneys, some goes here through the gut, some goes down here and goes through the liver, and then it all comes back together to re-enter the heart and go to the lungs. These organs are arranged in parallel, and that is a much lower resistance to flow compared to in series, and that makes things easier for the heart. We can describe this mathematically because resistances to flow add up differently when structures are arranged in series compared to in parallel. So structures arranged in parallel have a total resistance that obeys this equation here, where 1 over the total resistance equals 1 over the resistance of the first structure plus 1 over the second structure. In series, resistances add up such that R total equals R1 plus R2. So this is easier to understand if we put some numbers in. So let's suppose that we have 2 structures with a resistance of 2 and 2. We'll just arbitrarily assign them the number 2. What's the total R? Well, if we arrange these structures in parallel like the human body, then 1 over R total equals 1 over 2 plus 1 over 2. And if you solve this, R total is equal to 1. Now if we put those 2 structures in series, R total is R1 plus R2, which is 2 plus 2 plus 4. So look at this. The same organs with the same resistance, if arranged in parallel, have a resistance of 1. If arranged in series, the resistance is 4 times higher. So once again, parallel arrangement of structures is much more efficient because it lowers the resistance to flow, and this is why the human body is set up this way. Now let's go back to the flow equation that we talked about at the beginning of this video. Delta P is equal to flow rate times resistance. And let's talk about how you can use this to calculate resistance, cardiac output, or delta P for the body and the lungs. This is the way that the flow equation is often applied to the body and the lungs. And the reason it's so often applied to these two systems is because for both of these systems, Q is the cardiac output. The entire cardiac output goes through the lungs, and obviously the entire cardiac output goes through the body as a whole. So we can use the flow equation to estimate cardiac output, or if we know the cardiac output, we can use the flow equation to estimate what the pressure change or the resistance is. So if we're going to apply the flow equation to the body as a whole, the pressure change as blood moves through the body as a whole is equal to the pressure in the aorta, in other words the arterial pressure, minus the right atrial pressure. After blood has moved through all the organs and vessels in the body, it returns to the heart at a pressure equal to the right atrial pressure. The resistance for the body as a whole, as I said before, is the total peripheral resistance. You should know that it's also sometimes called the systemic vascular resistance, or SVR. These two terms mean the same thing. And then if we're talking about the lungs, the pressure change as blood moves through the lungs is equal to the pressure in the pulmonary arteries minus the pressure in the left atrium. After blood moves through the lungs, it returns to the left atrium at a pressure equal to the left atrial pressure. And the resistance as blood moves through the lungs is called the pulmonary vascular resistance, or PVR. Now there's a problem with what I've written on the screen here. As you may know, a normal arterial pressure in the body is about 120/80. So what number are we going to use for the arterial pressure? We need a single number to plug into the flow equation. The same problem comes up in the pulmonary arteries. A normal pulmonary artery pressure is about 24/12. So what single number are we going to use for the flow equation? This is not so much of a problem in the right atrium or the left atrium. Pressure fluctuates slightly in the right atrium, but it's very close to a single number pressure of about 6 or 5 or so. In the left atrium, the pressure also fluctuates very slightly, but it's very close to a mean number of about 10 or so. So we don't have so much of a problem in the atria, but we do have a problem in the arteries. We need a single number to plug into the flow equation. So if we're going to use the flow equation and we need a value for the systemic arterial pressure or the pulmonary arterial pressure, we need to calculate the mean arterial pressure. And you might think that the mean arterial pressure should be halfway between the systolic and diastolic pressure, but it turns out that's not the case. The reason for this is because our body spends more time in diastole than in systole. So the mean arterial pressure is calculated from the equation that mean arterial pressure is equal to diastolic blood pressure plus 1/3 of the difference between systolic and diastolic pressure. So for the total body, if a patient had a normal arterial blood pressure of 120/80, the mean arterial pressure would be 80, that's the diastolic pressure, plus 1/3 of the difference between 120/80, which is 40, and this would work out to 93. If we're talking about the lungs, and let's suppose a patient had a pulmonary artery pressure of 40/20, the mean pulmonary artery pressure would be 20 plus 1/3 of 20, and that equals 27. So this is how you calculate a mean arterial pressure, and this is what you need to do to use the flow equation for the lungs or the body, because the pulmonary artery pressure and the systemic arterial pressure fluctuate a lot. You need a single number to plug into the flow equation. So now let's talk about how we would actually use the flow equation to estimate some values for the total body. So for the total body, the resistance is the total peripheral resistance. The change in pressure as blood flows through the total body is equal to the mean arterial pressure minus the right atrial pressure. And just to make this very clear, blood leaves the heart to go through the total body with a pressure of the mean arterial blood pressure. The blood then flows through the entire body. It flows through all the organs in the body, and then the blood goes back to the heart, and the pressure when it comes back to the heart is equal to the right atrial pressure. So the delta P is the difference between these two values. So suppose we have a normal cardiac output of 5 liters per minute, and then let's further suppose that a patient has a blood pressure of 155/80, which gives a mean arterial pressure of 105, and then let's suppose the right atrial pressure is 5. From these numbers, we can calculate the total peripheral resistance. It's equal to the delta P divided by the cardiac output. This is all according to the flow equation. That's equal to the mean arterial pressure minus right atrial pressure divided by 5, which is 105 minus 5/5, or 20. And in board exams, they're always going to give you numbers that work out very easily, just like these. Notice that all the numbers you can basically calculate without a calculator and get an answer for the total peripheral resistance. We can do the same thing in the lungs. So in the lungs, the resistance is the pulmonary vascular resistance. The delta P is pulmonary artery pressure minus left atrial pressure. If we're given a cardiac output of 5 and a pulmonary artery pressure of 40/10, the mean pulmonary artery pressure is 20. The left atrial pressure is given as 5. We can then calculate the pulmonary vascular resistance, and if you plug all these numbers in, you will get a PVR that's equal to 3. And in many disease states, the PVR goes up, and there are many disease states where the TPR goes up or down, so this is why this flow equation is important. It helps us understand those disease states. And here I've summarized the variables that you need in order to apply the flow equation to either the lungs or the total body. So for both the lungs and the body, the flow rate is the cardiac output. The resistance to flow is PVR in the lungs and TPR in the body. The starting pressure as blood enters the system for the lungs is the pulmonary artery pressure. In the body, it's the mean aortic pressure. The ending pressure, which is the pressure as blood exits the system, is the left atrial pressure for the lungs, and it's the right atrial pressure for the body. And then finally, the delta P across the lungs is the mean pulmonary artery pressure minus left atrial pressure. For the body, it's the mean aortic pressure minus right atrial pressure. Now let's go back to that geometric equation I described at the beginning of this video that relates velocity and area to flow rate. So like I talked about before, flow rate in meters cubed per second is equal to velocity in meters per second times meters squared. And it turns out that area and velocity change as blood moves through different types of vessels. So the entire cardiac output has to move through the aorta and all the arterioles and all the capillaries and all the veins. All of these systems have the same flow rate, in other words, the same volumetric flow rate of the cardiac output. But the different types of vessels have different areas and therefore different velocities. And anytime the area for flow rate goes up, the velocity must go down according to this equation. So let's look at this table I've placed on the screen here describing the flow properties of different types of blood vessels. Flow is the same through all the types of blood vessels. There's no set that has higher or lower flow. All the types of blood vessels, arteries, veins, capillaries, have the entire cardiac output flowing through them. The total area for flow, however, is different through different vessel types. The capillaries, it turns out, have the highest area for flow. Even though capillaries are very, very small, there are millions of them in the body, and therefore the total area is very high. What this means is, by this equation, when the area goes up in the capillaries, the velocity goes down. So the velocity in meters per second of blood flow through the capillaries is very slow, and that's actually very helpful for gas exchange. The lowest area for flow is in the large arteries. This is counterintuitive. These are large vessels, so you might think they have a high area for flow, but there are actually relatively few of them, so when you sum up the total area, it's the smallest of all the different vessel types. Velocity is highest, therefore, in the large arteries and lowest in the capillaries. It's basically the reverse of the situation for area. The resistance to flow, as I told you before, is highest in the arterioles. Those are resistance vessels, and they have therefore the highest pressure drop as blood flows through them. The lowest resistance to flow is in the veins, and therefore the smallest pressure changes as blood flows through the veins. The most important thing to know about the veins is that they hold a large volume of blood. They are basically a storage basin for blood, and therefore in situations of volume loss, the veins can constrict and push more blood to the heart to help keep the volume status of the body normal. The last topic for this module is the law of Laplace. The law of Laplace explains the determinants of wall tension or wall stress. It can be applied to a blood vessel, but in this module we're going to talk about how it applies to cardiac chambers like the left ventricle. The reason the law of Laplace is important for understanding the left ventricle of the heart is because anything that raises the wall tension in the left ventricle will raise myocardial oxygen demand, and this can potentially cause ischemia or angina. So the law of Laplace states that the wall tension of the left ventricle is proportional to the pressure generated by the left ventricular chamber times the radius of the left ventricle divided by 2 times the wall thickness. The letter H is used to denote wall thickness. So now let's talk about some pathologic processes that can raise the wall tension in the left ventricle via the law of Laplace. Anything that raises the afterload of the left ventricle will increase the pressure that must be generated by the left ventricular chamber. This occurs in the setting of hypertension and aortic stenosis. These are the 2 classic conditions that raise the afterload on the left ventricle. Via the law of Laplace, when the afterload goes up and the pressure that must be generated by the left ventricle goes up, the wall tension will rise because pressure is in the numerator, so when it goes up, the wall tension goes up. This means that the myocardial oxygen demand of the left ventricle will be increased in the setting of these conditions like hypertension and aortic stenosis via the law of Laplace. This is called pressure overload of the left ventricle. If the preload on the left ventricle rises significantly, this can stretch the chamber and increase the radius of the left ventricle. This will increase the wall tension via the law of Laplace, because when the radius goes up, the wall tension goes up. This is called volume overload of the left ventricle. The two classic conditions to cause this problem are chronic valvular disease from aortic or mitral regurgitation. In both of these valvular disorders, blood is leaking through either the aortic or mitral valve, and therefore the left ventricle has greater preload, and this can lead to increased wall tension via the law of Laplace. The law of Laplace also explains left ventricular hypertrophy, which is a compensatory mechanism of the left ventricle to decrease the wall tension in the left ventricular chamber. Anytime the wall thickness goes up, according to the law of Laplace, wall tension will go down. The force inside the left ventricular chamber is distributed over more mass when left ventricular hypertrophy occurs. And this is commonly seen in settings of chronic pressure or volume overload. In my field of cardiology, when we take images of the heart of patients who have aortic stenosis or hypertension or chronic valvular disease, we see increased thickness of the walls of the heart. That is hypertrophy, which is a compensatory mechanism of the left ventricle. There's lots of basic science research that looks at the cellular mechanisms by which wall tension drive the myocytes to hypertrophy. You don't need to know all that for step one, but you do need to be aware that when the left ventricle hypertrophies, it lowers the wall tension and compensates for the increased pressure or volume overload occurring inside the chamber. Now, it turns out that there are two ways by which the left ventricle can hypertrophy in disease states, and it's very high yield to understand these, so let's talk about this now. The first way the ventricle hypertrophies is called eccentric hypertrophy, and in eccentric hypertrophy, basically what happens is the myocytes in the left ventricle become longer, and the reason they become longer is because more sarcomeres are added, and they are added in series. Let's look at my drawings on the screen here. On the left side of the screen, I've drawn a normal LV cavity of normal size, and it's got some sarcomeres present. When eccentric hypertrophy occurs, the LV cavity becomes dilated and the myocytes become longer. So if you were to weigh this heart in the middle of the screen, it would weigh more than the normal heart. That's because there is hypertrophy and the left ventricular mass is increased. However, if you measure the thickness of the walls, the wall thickness is not increased, and that's because the new sarcomeres are being added in series. The myocytes are growing longer, but they're not becoming thicker. This type of hypertrophy classically occurs in situations where there is volume overload of the left ventricle, basically when the left ventricle is flooded with blood volume. And the two classic valve conditions that cause this are aortic regurgitation and mitral regurgitation. You can also see eccentric hypertrophy in many forms of cardiomyopathy, including ischemic cardiomyopathy and non-ischemic cardiomyopathy. So when my patients with heart failure who have a reduced ejection fraction develop hypertrophy, the type of hypertrophy they usually have is eccentric hypertrophy. The second type of hypertrophy is called concentric hypertrophy. In contrast to eccentric hypertrophy, this typically occurs when the ventricle is pressure overloaded and there are chronically high pressures in the ventricle. If you look at the drawing on the bottom of the screen here, we've once again got our normal left ventricle on the left side of the screen. In concentric hypertrophy, you get something like what I've shown in the middle of the screen. Once again, left ventricular mass is increased. However, in this case, the LV cavity size is smaller, and that's because these walls have become thicker. And the reason they've become thicker is because sarcomeres are added in parallel. We've got increased myocyte size, but in this case, it's because sarcomeres are added in parallel, and therefore the wall thickness goes up. And remember, in eccentric hypertrophy, the wall thickness does not increase. So the two classic causes of concentric hypertrophy are systemic hypertension and aortic stenosis. In both of these conditions, the pressure inside the left ventricular cavity gets very high, and that leads to concentric hypertrophy. No one really understands the biochemical mechanisms that lead to eccentric hypertrophy in some cases and concentric hypertrophy in other cases, but the bottom line is these high pressure disorders like hypertension and aortic stenosis are associated with concentric hypertrophy. In addition, anytime you have concentric hypertrophy and thick walls of the left ventricle, you get decreased compliance and a stiff ventricle. And for that reason, in many cases of diastolic heart failure, which I talk about in the heart failure section, you see evidence of concentric hypertrophy when you do imaging of the heart. And that concludes our video on blood flow mechanics.